All right. Yeah. So thanks a lot for the invitation. It's great to be back here in Jerusalem. Indeed, today I'll talk about some recent work on relating these three things, which maybe seem like they shouldn't be related. So hopefully, at least by the end of the talk, I'll be able to convince you that they are related. Okay. I want to start by reminding you of three conjectural restrictions on low energy electromagnetism that we often think they should follow from the consistency of quantum gravity. So the first one is pretty easy. There must be charged states. So if you have a Maxwell field and it's coupled to gravity, then the only way for that to be consistent is if there are states that are charged under the Maxwell field. Not obvious from the point of view of writing down Lagrangians or low-energy perturbation theory. A stronger conjecture is that not only must there exist charged states, but there must exist states with all of the charges that are... We'll discuss. So far, I just said charged states, so this could be black holes. Yeah, I'll comment on that in a sec. For now, just saying, when I said low energy, I just meant if I just tell you, that there is, it makes sense to write down a theory of, at least classically or in perturbation theory, to write down a theory just of Maxwell coupled to the metric and nothing else.
We wouldn't think there needs to be low energy charged particles.
Well, I'll comment on that. Conjecture number one doesn't demand that. Yeah. Conjecture number two, a little bit stronger. So all possible charges, there must be states with all possible charges. Every charge allowed by charge quantization, there must be a state with that charge. So to be clear, throughout this talk, little q I'm going to use to denote the minimal unit of charge allowed by the topology of the gauge group U1. Okay, and then the strongest conjecture, now getting to what Andy was saying, is that not only must there be charged states, and not only must you have states of all charge, but actually you need to have a particle of charge little q, the minimal charge allowed by charge quantization, and its mass has to obey this inequality that m times square root of g, Newton's constant, must be less than or equal to q. Each of these conjectures implies the ones above it. And this third one is a version of what's called the weak gravity conjecture proposed by these people.
Equality is the same, would be achieved by extremely black holes?
Yeah, that's right. So that's how you fix the coefficient, which I didn't write. Yeah. The first two of these conjectures can just be satisfied by black holes. But I want to emphasize that the third one can't, at least if the gauge coupling is weak. You see here, if Q is much less than 1, then M is much less than M Planck. So this is saying that you really need a field to put it that you would put in your low energy action at some scale which is below the Planck scale. So in some sense, this is perhaps the most interesting conjecture. So, like I said, none of these can be derived in perturbation theory, but all three seem to be true in string theory, which is, in fact, I think, why probably the best argument so far in favor of them.
You mean it's supersymmetric string theory where it's saturated, or when we?
There are cases where it's not saturated. So, like I think in type 1 string theory, there's a gauge field, and the string states are quite a bit below the threshold. Okay. I should say that so far I don't find the arguments for these conjectures particularly compelling. I mean, it's true in string theory is in some sense a compelling argument, but it doesn't really get the sense of telling you why it's true. For example, if there are no charges, how do you make a charged black hole? Even if there are charged black holes, why can't they only have even charges? What's wrong with that? In particular, the original argument for conjecture 3 was that non-BPS charged black holes should be able to decay, but why, really? I mean, the argument given was that otherwise it would be weird. And, you know, I'm sympathetic to that, but you'd like to think that we could do better than otherwise it would be weird. In fact, they weren't even really able to even figure out what the conjecture should be. So they hemmed and hawed and eventually settled on a conjecture that's actually weaker than the one that I just said, where rather than insisting that the particle has minimal charge, they just said it can have any charge, and then its charge to mass ratio must obey this inequality. And that version actually can be satisfied by black holes. So what is the conjecture anyway? Now, just historically, I should comment that they also considered this version, and then they ruled it out based on a supposed counterexample, which is actually incorrect. So I think it's just a historical artifact that this is the version which was considered for the last 10 years. And they acknowledge that the counterexample is really an example. For the rest of this talk, what I'm going to do is I'm going to describe a paradox in ADS-CFT whose resolution seems to require all three conjectures, and in a way that I think gives more intuition as to why they should actually be true. So full disclosure, so my arguments for conjecture 1 and 2 are quite general, and I'm pretty sure they're correct. The argument for conjecture 3 depends a little bit more on the details of how I resolve the paradox, although I think it's still getting at the heart of the matter. And so essentially everything will be based on this paper from last year. I should comment that since then there was another paper by Jafris and Guica which discussed some aspects of these same things, although they took things in a different direction in the end. And then also I guess Hiroshi and I are working on setting these arguments in a more general context. So for this talk, I'll always be talking about U1 gauge fields. But
Conjecture is that there's a particle of minimum charge that obeys this.
That's correct. Yeah, that's correct. Yeah, and that's and it's really essential that that's the. I mean, actually, this version doesn't even apply conjectures 2 and 1. But for my resolution, it's going to be essential that it's a particle of minimal charge. Okay. So now let me just first remind you that in ADS-CFT, recently there's been a lot of progress in representing fields in the bulk as operators in the conformal field theory. I guess most of you by now have heard plenty of talks about this. But just very roughly, the idea is, so say phi is a bulk field and say it's dual to a CFT operator O, in the sense that if you take phi and you pull it to the boundary, it becomes some rescaled version of O. So then by perturbatively solving the bulk equations of motion, you can represent an operator in the conformal field theory whose correlation functions reproduce the bulk effective field theory correlation functions of phi by integrating it against O with some kernel and then perturbatively generating corrections. So this works also when you have gauge fields. The only new subtlety is you have to make sure to talk about gauge invariant operators. So for example, this here is a Wilson loop. You can also have a Wilson loop that starts and ends on the boundary, or you can have a Wilson line between two charged operators, or a charged operator with a Wilson line attached to the boundary, or you can just have a local neutral operator. Those are all sorts of gauge invariant operators you can have. In particular, all of these operators, well, maybe except that one, involve the gauge field in some way. And using the same kind of machinery, you can represent them in the CFT in terms of the current, which is dual to the gauge field via the same kind of operator dictionary. So in particular, we should note that a global symmetry in the CFT becomes a gauge symmetry in the bulk. So this J mu is the current of a U1 global symmetry in the CFT. This is consistent with the idea that there shouldn't be bulk global symmetries. You see that a global symmetry in the CFT is actually gauged in the bulk. Now, what I'm going to focus on today is reconstructing these gauge invariant operators in a different background, the ADS Schwarzschild geometry. The reason that's interesting is because there's now a new kind of gauge invariant operator that we didn't have before. You can have a Wilson line that starts on one end of the boundary, goes through the wormhole, and ends on the other boundary, if you like, in the other conformal field theory. And the interesting thing is that this operator cannot be reconstructed in the CFT using the techniques that I just described. The basic problem is that the Hilbert space of the CFT factorizes into a tensor product structure of the left CFT and the right CFT. And we think of this state as corresponding to the thermal field double state of that system. So in particular, any operator on this Hilbert space is a sum of tensor product operators between the two sides. So that means, if you like, that any operator can be cut into the left piece and the right piece. But with this Wilson line, well, at least if you try to cut it in the naive way, so you take the part that's on the left side and you take the part that's on the right side. And here, just to establish notation, by W little n, I mean the Wilson line in the n representation. You see that the pieces aren't separately gauge invariant. They're only gauge invariant once we combine them into the whole operator. So this prevents any attempt of trying to make, say, the left part out of J in the left CFT and the right part out of J in the right CFT. Because anything we make in the left CFT has to be separately gauge invariant, because everything in the left CFT is gauge invariant. Right there, this is the actual Hilbert space. So any operator we write down on it. Well, here I'm talking about I'm talking about an operator here, right? I mean, it's an operator that acts on Hilbert space. So, I mean, remember, you can't have a Wilson line ending on a charge, right? So ending on a charge field. So if you have charge fields. But I think this will be more clear as we go on. So maybe just hold off for a little bit, and hopefully it'll be clear. Yeah, no, this is just saying that at the moment, this is just a statement about solutions of Maxwell's equation. If I give you J mu at the boundary and you try to solve it inwards to construct A mu, you're not going to be able to produce this operator by doing that, because there'll be a Wilson link in the center that you can never get to. What? Oh, global, of course. Yeah. Yeah. Oh, this is absolutely normalizable state. Yeah. Okay. So this problem with factorization, we can get some intuition for it by remembering what happens just in pure electrodynamics. And I'm going to study it, pure QED, on a spatial R times S2. Okay, so a spatial cylinder. Now, the thing that's interesting is that by using the Gauss constraint, we can see that the integral of the electric flux through some particular two-sphere, say this one, is actually equal to the integral of the electric flux through another two-sphere, this one, as an operator equation. So in all states in the Hilbert space, this is equal to that. And from the point of view of quantum field theory, that actually seems a little bit weird, right? You're saying that two macroscopically separated operators are equal operators on the Hilbert space. It's somewhat in tension with this intuition that quantum field theory describes independent degrees of freedom here and there. And of course, this, you can trace it back to the statement that gauge theories are in some sense non-local. But this is a very macroscopic demonstration of that non-locality. In particular, if you tried to cut in the center of the cylinder, you wanted to spatially cut the cylinder in half. This tells you that it's never going to be possible to factorize the Hilbert space into a part on the left and a part on the right. Because were you to be able to do that, Well, the only operator that you have which is in common between two different tensor factors is the identity. And this is clearly a non-trivial operator, right? It measures the electric flux going down the cylinder. Times time, yeah, that's correct. This is a spatial R times S2, and then times time. Yeah, so I'm thinking of this in a Hamiltonian formulation. Yeah, and in fact, R2 times S2 is the same topology as this, so that wasn't a coincidence. That's why I picked it. Yeah. Okay. So this fact that roughly speaking, the microscopic Hilbert space, the boundary Hilbert space factorizes into H left and H right. Well, the bulk Hilbert space doesn't factorize. I call the factorization problem. At least naively, it seems to be in conflict with the idea of ADS-CFT. Now, obviously, the conclusion isn't going to be that ADS-CFT is wrong, don't worry. But at least it's something that we have to understand. How is this tension resolved? Now, we can begin to get a sense of how it's resolved by studying the algebra of Wn, this Wilson line in the charge n representation, with the asymptotic charges q left and q right. So q left and q right, you can either think of them as the integrals of J0 in the left and right CFTs in the CFT language, or you can think about them as the electric fluxes through the boundary two spheres in the left and right CFTs. So, just by doing trivial electrodynamics, you can see that the commutator of q left minus q right with Wn is this. So what that means is Wn is a creation operator for 2n units of ql minus qr. So if I act with Wn, I make the wormhole a little bit Reisner-Nordstrom. That's what this operator does. It's a very physical thing for it to do. Which also hopefully convinces you that it actually has to be there. And so the solution can't be we just say it doesn't exist. Okay. But now let's think about that, right? So then if we look, we can take the expectation value of QL minus QR in the state where we take the thermal field double and act with this W, and it's no big mystery. We get 2n. And in particular, 2n is not 0. Now, since we know that the Hilbert space factorizes, and we know that q left acts on the left factor, and we know that q right acts on the right factor, then clearly, and in fact, they're going to be the same operator abstractly, because it's just two copies of the same Hilbert space. So then we've immediately discovered that q can't be 0, which means that there must be charged states just in one copy of the CFT living on the sphere. So that establishes conjecture number 1. Yeah?
Did you sneak in a charge to the Wilson loop?
No, I mean, this argument, the only thing I used here were things made out of the gauge fields, right? The Wilson line is the integral of the gauge field. No, the Wilson lines don't have Q's. Wilson line, yeah, it ends at infinity. So remember, the boundary conditions at infinity allow Wilson lines to end on them. Well, it's a choice of boundary condition. This is the standard quantization of the photon, in which case you have a global symmetry in the boundary theory. There's also an alternate quantization of the photon where you don't allow the Wilson line to end at infinity. In the CFT, that corresponds to gauging the current. No, and well, okay, no, because I defined n here in terms of the n is an integer, because remember the gauge group is always U1 for me, and so
that's just the restatement of the assumption. As long as we just say it's
yeah, I mean, I guess I could have considered the case with the gauge group R and still made this argument, and then n could have been anything. I mean, now I should say that once I get to the next step of the argument and I argue that there needs to be states of all allowed charges, then if you want the gauge group to be R, you're in trouble. Yeah.
Wait, so we are already at 60 years ago with black holes, the charge state by wormholes.
Yeah.
When you have wormholes. And
Well, no, but they always come in pairs, right?
no. You could pull one pair infinitely far away. So
well, if you,
that would you know. So then now, why isn't this just a more sophisticated version of that? I mean, I could have said, but I'm not allowing you to consider Wilson. I mean, you're just saying that once you admit that you're going to talk about the action of Wilson lines on the theory, then you're allowing for fluxes to thread black holes. He said that classically.
yeah, no, yeah.
Well, if it's true classically, it should be true.
No, but it's essential. The factorization is essential here because in this example there aren't charges, right, in QED on the cylinder. So this is a perfectly consistent theory where this Wilson line exists and there aren't charges. The only reason I found that there need to be charges in the CFT case is because I know that there's a way of cutting where it factorizes into the left and the right, where the flux at this end acts on the left and the flux at this end acts at the right. Now you're essentially assuming that by saying that you can pull the black hole away to infinity and forget about it. And I mean that's fine. I'm not opposed to saying by some sort of cluster decomposition, then it seems like there should be some charges. But I think what I said is a much more rigorous argument. I mean, if we want it to be Wheeler, I think if you're willing to consider unorientable topologies, you can come up with charged geons. But I don't know. That also seems a bit fishy to me. I don't know. Maybe those make sense. Maybe they don't. But I mean, no. I'm not. I mean, all three of these conjectures are pre-existing, right? I mean, I think this is a better argument. That's all I'll say. I don't want to say that there were no other arguments previously. I want everything. I mean, the CFT is the real thing. So I want everything to be a CFT operator. But I mean, to be clear, just in case anyone is confused, I'm never talking about Wilson lines of like the SUN gauge symmetry in the boundary theory. I'm always talking about Wilson lines in the bulk of a U1 gauge field in the bulk. Yeah. Yeah. But what's in the other side? No, I do care. No. Well, I mean, it's not that different, but no, I think, no, from a purely, no, I don't think so, right? Because the factorization is essential, right? Like in quantum electrodynamics, you can have this, and there are no charges. No, but you have this. The topology is the only relevant thing, right? I mean, the new thing that isn't here just from the point of view of thinking about gauge fields propagating on this background is that you can cut the Hilbert space. Let me continue because I think it will be more clear as we go on to the extent to which this is different from that argument. Okay. Now, let me first say that once dynamical charges exist, I can no longer make the argument in QED that I made before because now the Gauss constraint has something non-trivial on the right-hand side. Del dot E is equal to rho instead of equal to 0, so those electric flux operators can't be equal. And in fact, I want to argue that once we have dynamical charges, this postpones the factorization problem into a UV question. Before it wasn't a UV question. We had these macroscopically separated operators that had to be equal. But once we have charges, it becomes more subtle. So roughly the reason is that we have this Wilson line, but we can also have a Wilson line that ends on a charged operator, and then another charged operator here, and we keep going. And this operator behaves a lot like that operator in low-energy correlation functions. So it becomes harder operationally to say whether the theory does or doesn't have the Wilson line or what it means. So to make this precise, I want to first revisit I want to discuss the factorization problem in 1 + 1 dimensional lattice gauge theory, which is sort of the essence of this. The sphere is irrelevant. So let's think about 1 + 1 scalar electrodynamics. We have lattice sites in a line going from 0 to n. So I'll have charge fields living on the sites, and then gauge fields living on the links. They're gauge transformations, so the charge fields get rotated. The Wilson links have this conjugate transformation. And the boundary conditions I'll pick to be similar to QED in ADS is that the gauge transformations are trivial at the two ends. And then just to be concrete, can put Dirichlet boundary conditions on the scalar. Okay, so here are some gauge invariant operators. So the star of the show, the Wilson line, we just take the product of all the links. There's also electric fluxes on each link. There are operators we can call phi right and phi left, where I put a charge field at phi I, and then I run the Wilson line to the right boundary or to the left boundary. There's a charge density operator made out of the phi's. And the Gauss constraint is just this discrete version of Gauss's law. So now say we want to cut the Hilbert space between site L and site L plus 1. We can solve the constraint, because we're in 1 plus 1 dimensions, to write an arbitrary gauge invariant state like this. So every phi who is to the left of L, we dress to the left. And every phi which is to the right of L, we dress to the right. So these phi left operators are all commuting with all of the operators on the right. And these phi right operators are all commuting with all of the operators on the left. So we've almost got a tensor product structure, but not quite, because we've got W hanging around here. You can phrase this more rigorously by saying that the algebra of operators associated to either side has non-trivial center and therefore can't correspond to a tensor factor of the Hilbert space. So what you learn is that, well, we haven't solved the factorization problem by introducing charges. We made it somewhat, maybe we made it better, but it's still there. We had to put in a cutoff to really decide for sure whether the Hilbert space factorized. But at least in this cutoff, the Hilbert space doesn't factorize. Okay. Nonetheless, the situation has improved. So as I said before, although W is still confusing, we now have this operator W prime, where I go from one side to phi L, and I put a charge there, phi dagger L. Then I do a phi L plus 1, and then I keep going. And I claim that this operator behaves identically to W in low energy correlation functions. So let me... Yeah. So I can justify this claim that they're roughly equivalent by doing a kind of gauge covariant operator product expansion, where I say that if phi dagger of x, phi of y, in the limit that they come together, they can be replaced by the Wilson line from x to y times some C number function plus less singular terms corresponding to less singular terms in the operator product expansion. You can check this perturbatively in Q squared in electrodynamics, and you can also, in the case of conformal field theories, derive it rather generally using the usual kinds of arguments you used, inserting complete sets of states and so on. So I did some of that in my paper, and then just this week there was a paper by Abhijit Gade who was explaining how to do some similar things. We can also make this look a little more gauge invariant. Maybe this looks a little annoying to you. So we can move the Wilson line to the other side, and then this is like a short string expansion. So we have a string, electrodynamic string connecting two charges. We can draw a circle around it and expand in terms of local operators. The identity should win at short separation. Okay, so that then leads us to a rather simple proposal for how to represent W in the CFT. The idea is that you give me some correlation function or something involving various gauge invariant operators, of one of them being W. Then the idea is, well, instead of using W, use this instead. And because of this operator product expansion, you'll get more or less the same answer. But now, you see the left and the right pieces are separately gauge invariant, so there's no further obstruction to representing this piece in the left CFT and this piece in the right CFT. And in fact, you can do that using the standard technology. Now, let's just make a few comments that follow immediately from that. So first of all, in order to cut a Wilson line in the fundamental representation, we need an operator of charge 1. So there must be a state of charge 1. So this implies conjecture number 2. So we're 2 out of 3. Secondly,